Okay, now we're talking about AC. You already learned more. You already know something. We can go quickly. Okay, this is the AC signal. I try to identify what we picked. Okay, pick to pick the IMF period frequency. Okay, and basically definition. So we already get through that one. Okay, next one. This is a capacitor. Okay, capacitor is a circuit component designed to store electrical charge. If you connect a DC voltage source to a capacitor, the capacitor will charge to the voltage of the source. The capacitors are widely used in electrical and electronic applications. They are used in electronic systems for signal conditioning and timing. Capacitor could be either non-polarity or polarity. Normally, value of capacitor is farad, millifarad, microfarad, nano, and picofarad. Okay, if you're looking into here, you already get along. Okay, which look like the capacitor. Okay, if you get any question, anything, just stop me. Okay. Now, we're talking about capacitor charging. Okay, so you can see this is a circuitry here. Okay, you get a switch. They can connect to position 1 or position 2. Okay, now if they connect to position 1, look like this one. Okay, so the voltage E voltage get a current I. They go through resistor, and now they're charging capacitor. Okay, so you see how they display. This is a time domain. This is the amplitude for voltage VC. At the beginning, voltage is 0. Okay, and when the time going up, the voltage charging keep going. Okay, up to a certain point here. Okay, that's what they call transition interval. Okay, up to this point, they have no charge anymore. The thing is the voltage on the capacitor and the power supply E voltage, they be the same. That's why no more current can be flowed. Okay, so that's for charging. And now they're showing you YIC equals 0. The thing that the voltage on the capacitor and the voltage on the E power supply, the same. So that's why no current can be flowing. Say IC equal 0. Okay. Another one, equivalent circuit for the capacitor. Okay. So basically, when they be full charge, like they open, they get a positive voltage here and negative voltage here. Time constant. Time constant, tau equal R times C. In this formula, R in ohm, C in farad, and tau in second. Time constant is the time for capacitor charge or discharge to 63.2% of the maximum value. Okay. And after 5 time constant, capacitor will be full charge. Okay, so now we're talking about capacitor discharging. Now they move, okay, the switch to position 2. That means the round here, okay? So now capacitor will be power, okay? And the current will be flowing from capacitor to the round. They draw this way. That means electronic current, okay? But we're using a conventional current flowing from positive to negative, okay? And if you're looking on display here, this is the charging. Okay, it's the charging. And they start discharging. Keep going down, okay? Until nothing, 0. So now you can see the signal on the capacitor charging and discharging. Okay? The red capacitor charge is depending on the product tau equal RC. That's what they call a time constant. Time constant is the time for capacitor charge up to 63.2% of the maximum value. Tau equal R times C. Remember, that is the time for capacitor charge up to 63.2% of the maximum value. However, they say after 5 time constant, capacitor will be full charge. Okay, let's see. This is a formula to calculate, okay, voltage charging or discharging, delta VC equal one time minus 1 over E to the power T over RC. Okay, this is a formula to calculate the voltage charging or discharging on the capacitor. Okay, in here, they explain to you E, voltage difference between Okay. E voltage difference between the initial voltage on the capacitor and the total voltage that it is trying to reach. That means power supply. Small e natural logarithm equal 3.7. T, time that capacitor is allowed to charge, R in ohm, C in farad. If you want to calculate the voltage charging on the capacitor, that means you have to using this formula. Okay, so for the example here, you get 40 volts, 200 ohm, 1000 microfarad. Okay, do the following calculation for the circuit show when the switch is low and capacitor is discharged. First thing they want to calculate the time constant. Now, what you can do for me, do calculation to see you can get 0.2 second or not. How constant, you know that equal R times C, right? And number 2 will be at 5 time constant. What the voltage? Okay, try to see how many people can get the right answer for me.
40.
First thing, number 1, time constant. That means you take R, you times C.
Wonderful.
I have to be in O. C have to be farad. If you get a 0.2 second, let me know.
$200 thousand.
Anyone get 0.2 seconds?
Well, wouldn't it be 200 times 0.001? Or am I totally off there?
Is it 0.2 seconds?
Yep.
Yes.
Yes.
Okay, correct.
Okay. Thank you.
Now, VC at time constant. That means at 5 time constant, what VC equal. So you know the formula, they calculate the VC, right? E times 1 minus
1 times 1 minus 1
Mm,
divided by,
Over, 1 over.
I'm having a hard time seeing. So two. Hmm. Oh,
First thing what you need to do, calculate T over RC first. Okay. This means we want RC. Then T over RC.
Ah,
okay.
Basically, you try to understand. We not go to too many details, like you have to do a calculation. Okay? The big thing will be understanding. Number two, VCS time constant. Time constant, that means 0.2 second.
Yep.
So you calculate, could you get 25.28 volt?
Oh, oh, 谢谢你。
Easy way to do. First thing you have to calculate what RC equal. And T divide RC. Okay? T 0.2. Most likely you have to deal with the unit. You have to converting pico-microfarad to farad. Okay? The thing R have to be in ohm. C have to be in farad.
The 0.001.
I think the answer will be 25.28.
Oh,
Are you tired, Kristen? Christina?
I'm sorry. Oh, I'm sorry.
I'm tired too. You're making me want to yawn.
I thought I already knew. I'm sorry.
Okay, no problem.
Thank you for reminding.
No problem.
Who get 25.28?
I think can you show us steps to the problem?
Okay, you see that you want to calculate the capacitor voltage. Okay, then you have to using the formula.
Mm-hmm.
So first thing we have to calculate R times C. R will be 200. C 1,000
Mm-hmm.
microfarad. Now we have to change it into farad.
Mm-hmm.
Basically, you know, farad 10 power of 6 microfarad. And now you get a 1,000. 1,000 means 1 times 10 power of 3, right? And now you will want to change it into farad. Okay. Then you can get 1 10 power of minus. Okay. Farad times 10 power of 3. That given you 10 power of 3.
Yeah, but isn't 1,000 microfarads equal to 0.001 farad or farads? 0.001 farads? Oh, okay, yeah, there we go. Sorry, I didn't see the negative sign. Thank you. Mm. 0.9997. No, I, I did something wrong.
Yeah,
What?
25.28 volts. I got.
Yeah.
Okay, you get
Yeah, I got.
25.28.
Yeah, is it?
Perfect. Number 3, they want the time VC Zurich for volt. You understand the VC equal time. Okay. This is the formula. T equal RC time log of 1 over 1 minus delta VC over E. Yeah, this really the top on calculation. Have to be very patient. Okay, let's see. D equal RC time log of 1 over 1 minus delta VC divide to E. RC you already know. Delta VC. They say the time to reach 4 volt. So 4 divide 40. Okay, if you're doing a right one, then the time 0.02.
Yeah, 0.02.
Okay, perfect. So basically, the last one, they say after 30 milliseconds, the voltage capacitor, okay? If you know how to do, then you can get 4.17. However, you know, even myself, I get tired to working with this type of the calculation. Okay, so make sure you understand it. That's it. And you never have to do calculation. Okay.
Okay.
Now, this is the one you have to know. Capacitor in series. C1, C2, C3 connect in series. And now you want to get a total capacitor. Then they will be same formula like resistor in parallel. That means 1 over
understand.
1 over C1 plus 1 over C2 and so on. This is same as resistor in parallel.
Right.
And now, if you get only 2 capacitor in series, you're using C1 times C2 divide C1 plus C2. Exactly the same resistor.
Right.
Okay?
Okay.
And now, capacitor in parallel. If you want total, add them up. Okay? That's same as resistor in series. Okay, so basically, capacitor in parallel, they're working like the same resistor in parallel. Now, what I said, the capacitor in series, they working like resistor in series formula. Capacitor in parallel, they working like resistor in series. Okay? Now, on that one, they want to substitute C1, C2 by one resistor. Then they in parallel, they working like series resistor. So C3 equals C1 plus C3. So now, if you're looking from here into the circuitry, they want the total, okay, capacitor. First thing you have to combine this guy to one. So you know that one here. They parallel, right?
Yep.
C23. C2. Time. C3. Divide. Okay. And now you combine this guy. C4, 5. C4. C5. C4. C5. And finally, you can get C1. Then you can get C23. Then you can get
C45.
5. Good. C45. Okay, they in series. Now the C total. If you're doing a right thing, I think you can get that one. If you get it, let me know.
Hello, perderé y contigo como se tiempo. Okay.
Teacher, the capacitor in parallel is C1 plus C2.
Okay, maybe I get a wrong one.
So shouldn't that be additive?
That one and that one parallel.
So you just
Parallel
add
when
it.
you combine
Yeah, that,
C1 plus C2, okay?
yeah, that's what I was gonna say.
Yeah.
Something wasn't right because added together, it didn't come up to 12.
C2 plus C3.
Yeah, they're parallel.
And I'm sorry.
No, it's okay. It's been a long week.
C4, 5. C4.
Yeah, 12 microfarad.
Okay, perfect.
Yes.
In that one, the C total. Formula equal 1 over
Yeah.
1 C1. 1 C2, 3. C4, 5. And the answer will be 12. That one,
Yes, it's 12.
that one you need to know how to do calculation. Something you get a job interview. They just asking you, they given C3, C2, C3, and they want what the total. You should know how to do it. Easy. But they don't have to do calculation. Like calculation, the voltage charging on the capacitor, that's too long. Even they don't know either. Okay, any question about this example? Okay, if it's not, you cannot get it done. I recommend you spend another time to working on that. Okay, now they're talking about capacitor current and voltage during charging. So you see that current flow, charging VC. Okay, And now this is the IC. Okay. At the time 0 here. Okay. IC will be maximum before charging. Okay. IC will be maximum. Now, when the voltage charging is going up, and the current will be going down. And when the VC reach E, then the current will be 0. So you can see here, current at the top 0, maximum. When the voltage capacitor goes up, current going down. Up to this point here, that means no more charging. Then the current here will be 0. Okay. Okay. So what they tell you before charging, maximum. During charging, current keep going down. After charging, current look like 0. The question is, why the 0? Okay. I can explain telling you. That means after the full charge, the voltage VC and VE will be the same. So that's why no current flow. In here, they already tell current is 0 when full charge. That means VC equal E. And now they show you the voltage. Okay, we already know 0 here at time 0. VC will be 0. When they start charging, VC keep going up. See that?
Mm-hmm.
Up to a certain point, stable, no more charging. The thing is VC and VE equal. Capacitor voltage VC equal VE when fully charging. Okay, now another thing we need to know, radian. Measure in practice omega, usually expressed in radian per second, where radian and degree are related by identify joule pi. Radian equal 360 degrees. Now, if you see this is a sideway, 0 degree here, 90 degree, 180, 270, and 360. And you have to know about the pi. 3/2 equal 90. Pi equal 180. 3/2, 270. 2 pi, completely 360 degrees. Okay, you need to know the relation, okay, between radian and degree. Relationship between omega t and f, omega t equal to pi. radian. Omega equal 2 pi over t. That means radian per second. Omega 2 pi f radian per second. Note that omega is reference to at radian frequency. Now we're talking about capacity circuit. When AC signal sinusoidal applied to the capacitor circuit, the capacitor creates a resistance called capacitor reactance, Xc, represent the opposition that capacitance present to the current for sinusoidal and calculate in the following formula. Okay, now for capacitor, before we already learned, capacitor for DC, they will be open. For AC, they will be short. Okay? So when capacitor using the AC, they get the resistance. That calculated by the formula here. X equal 1 over 2 pi Fc. In this formula, pi equal 3.142. F will be in hertz. The real relation between capacitor voltage Vc and capacitor current IC for purely capacity circuit current lead voltage 90 degrees.
Rồi vĩnh biệt người thơ ngày buồn đau ngày giây phút mỗi sao người tình đau.
Someone asking me, no Zoom access in room 241. You understand it? Friday, Thursday, all the class will be low. Only in the Zoom, okay?
What day? Can you say that again?
I said, you already know. You only coming to the class Monday, Tuesday, Wednesday.
Yes.
Thursday, Friday, all the class will be low. Right?
Yes.
We're not open up there.
Right. Only Zoom.
Right. Only Zoom.
It may have thrown some people off though because Monday was a holiday. It almost threw me off. I asked your brother, I said, "Oh, what time the door open on tomorrow?" And he said, "Oh no class tomorrow." I was like, "Oh, thank you for telling me." So I'm glad I asked. I had forgotten that Monday was a holiday and not Sunday.
It can be confusing, you know.
Yep.
What you need to remember in here. Current IC lead VC 90 degree. That is, you have to know. And also, this is the formula. To calculate the resistance of the capacitor when you connect into AC circuit. Okay? SC, SDC equal SC, SAC. Now, SC equal 1, 2 pi FC 1 over what? What frequency on DC?
0.
Is it
One.
over time?
What frequency for in DC?
0.
0.
0.
0 times 2 pi times C will be 0. 1 over 0 equal
Infinity.
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 Okay?
Too high.
That means open. So, for capacitor with a DC, they will be open. Same thing. Now, if the AC one over 2 pi F, what F equal? AC.
Frequency different than 0.
60.
You can say that it could be 1 kilohertz, right?
Something.
100 kilohertz. Okay? Any frequency I given to you infinity.
1-0.
Perfect. 0 ohm. They will be
Short.
short. Okay? That only telling you one thing. Capacitor open for DC. However, they will be shorted for AC. And also, you must be memorized. The current IC lead voltage VC 90 degree. Now, if you're looking on that one, okay, this is the VC. And this is AC current. You see, they go in here 90 degree. First. So that one telling you, okay, IC lead VC 90 degree. For circuitry in first one here, they want capacitor reactant XC. Okay, you calculate XC for me. What XC equal? Okay, calculate it and telling me what you get. Who get the answer?
Two point 12 kilo ohm.
How many ohm?
2.12 kilo ohm.
2.2 kilo ohm.
2.12 kilo ohm.
Okay, so
2.35.
is it right?
Maybe I did something wrong. I got 2.35.
I already gave it to you here. 3.14 joule times 1.5 power 3 times 0.05 times 10 minus 6.
Okay.
One student get 2.1 joule. Okay.
Kilo ohm.
Kilo ohm, right?
Yeah, kilo ohm.
Well, You get 2.12.
Yep. 2.12.
Kilo ohm. Look like I get 4.24. How come I get 4,243? Okay, you get the same answer to me or no? Only thing is you substitute into here and do calculation. How come it takes too long?
Mr. Pham, it's 2 pi.
Get 4.20 for kilo ohm or 4.25 kilo ohm.
Oh. Oh, yeah.
Okay. Anyway, you have to take your calculation. And the next question, they want to calculate the current I. So when you get the HC, capacitor resistance, then you just using Ohm law. I will be VT divide $100 4.24. Just Ohm law. And so will be 23.4 milliamp. Okay? And now we go to example number 2. I just given you the way to calculation. We don't want to wait too many times. And now, for circuit number 2, they want to calculate the capacity reactance. Let's see. Okay. You already get the current and the voltage VT divide I. So they will be 10 volt divide 20 times 10 minus 3 ampere. That's it. And then they want to calculate the C. Okay. IC equal 1 2 pi FC. From this formula, you can calculate C equal 1 over 2 pi f xc. That's the formula to calculate the capacitor. Right now, you don't have to calculate it. You need to make sure you know how to working on. Now, you can see the difference. Capacitor in series and parallel. However, the difference here you can see the difference.
Yep.
The difference here will be XC1, XC2, XC3. They look like resistor. So parallel or series, they working exactly like the same resistor. Okay? If they don't have a XC, they're using the value of C. They opposite to the resistor. Okay? XC are in series. Okay, we try to get through that part here, and we will be stopped. Okay? This is a series circuit. Now, I see. That means capacitor will be get. I see. R will be 60. Fourth one, current IT the same on the component, for sure. Right? That will be the same. The voltage VR, that means the voltage here, VR, is in phase IT. Okay, you understand me? VR I T times R. So for the resistor, voltage and the current in phase. You understand what that means in phase? Now I show you. If you get VR IR, that means both going up, both going down. They go in phase. Okay? You understand in phase.
Mm-hmm.
Resistor have a no phase different. However, if we're talking about VC, okay? So if you get that is VC, okay? Now, where is the IC? We already know,
It leads it by 90 degrees.
okay? So you understand it is 90 here, 180, 360. So IC leading VC 90 degrees. So IC will be go here. That is IC leading. Okay. If you're reading here, okay, IC lead VC 90 degrees. Also, VR IT in phase. So that will be telling you VR lead VC 90 degrees. So you understand why we are lead VC. The thing is, IC and VR in phase. Okay? So that's why we are lead VC 90 degrees. Okay? That's why number 4, they explain to you. Okay? VC equal IT times XC. VRIR times R. XC and R must be 90 degrees of phase. Okay? That means we are lead VC 90 degrees. Now, you can see this is you draw for VR. R. Okay? This is a leading 90, 180, and also 90, minus 90. So you draw the vector or the rectangular coordinate. You draw R here. Then XC have to be going down. Why? The thing is R leading XC 90 degrees. Okay? And now you draw the phasor here. You draw R here. What thing? R. XC going down here. Okay? You connect this point to here. You get the Z total. Okay? If you want to calculate the Z total impedance, will be square root of R square plus HC square. That's a Pythagorean formula. If you want to calculate the VR, IT times R, VC, IT times HC. If you want to calculate the tan of the theta right here, okay, you know that formula. Minus VC divide R, and you want to calculate the angle, okay, take tan minus 1 minus HC over R. IT will be lit VT, 0 degree. That covers everything for the series RC circuit. Okay. Now, 1000 ohm, HC 1310 ohm. Total impedance, what Z equal? Total current. Now let's see. Z total here, sorry. That's coming out from this formula right here. Voltage VR.
IT times R.
Angle. Okay, 10 minus 1. This is the one they help you to calculate that. Now, this is the first time of the AC. And you know you get two circuit board you have to do. AC1 and AC2. Okay? Normally I be in the class on Monday. If you get a problem, let me know. I help you.
Okay.
Only thing is we don't care pass or fail, but we care. You understand or not?
Thank you.
Okay, that's what I want to help you. Even I don't have to be up there, but I run this program. I want the student coming out easy to get a job. Okay. Any question? Anything else?
Oh, thank you.
Okay, then we'll see you on Monday.
Okay.
Good night.
Hey, bye
Have a
bye.
nice
Good night, sir.
weekend.
Bye-bye.
Thank you so much. Have a good one.
Bye-bye.
Have a good weekend.
Good weekend.
You're
Okay.
gonna post this recording, right?
Yeah.
Okay, thank you. Have a nice weekend.
You too.
Thank you. Bye-bye.